usually try to record these lectures and put them on YouTube, so if you want to see what we've done other days, you can. So I'll begin with a word of prayer. So, Dear Father, we thank you for this day. Again, I thank you for the visitors, and just pray that you bless this class, help us to glorify you what we do learn. In your name I pray, Lord Jesus. Amen. All right, so since you guys took the time to take the quiz, I figured I should probably show you the solution. We don't always do this, so hopefully I'm right. I don't know. We'll find out. My computer will behave. Come on. All right. All right. Let's see if this works. Well, there it is. This only works if you plug in the computer, you know? All right, so for problem 1, I decided to treat it as a graph. All right, and so used x and y as parameters. Then, of course, we can solve for z is 1 minus x minus y. Since we're inside the cylinder, the domain for the parameterization we should take to be basically radius 0 to 2 for the disk. When I calculate the normal vector field to the surface, take the cross product of the partial velocities, the result is very unsurprising, right? Because we're dealing with a plane which is part of a surface, so of course I will eventually get a new laser. This has never happened before. Okay, that's a lie. Man. You have one job. There we go. So not surprisingly, 1, 1, 1 is the normal because, of course, it's a plane. As you guys learned in like week 1 or 2, the normal to the plane is 1, 1, 1, right? So that happened. And with that in mind, I calculate the surface integral. I take the integral over the disk of this function, where z is, of course, 1 minus x minus y. And so I take the dot product. Basically, then I plug in the formula for the parameterization into the vector field. And when you take the dot product with 1, 1, 1, you just add the components. So that's what happened. And some details. So basically, I just multiplied that out. That's where I probably made my mistake, if I did make one. And let's see here. When I did that, things collapsed down. Eventually, I get 5 minus x minus y plus x squared plus y squared plus 2xy. Now, x and y clearly integrate to 0 over the disk because they're positive and negative on the half one side of the disk and the other. And of course, you could also say the same about 2xy, but I didn't bother yet. X squared plus y squared is r squared. Now, of course, if I'm integrating over a disk, I don't want to actually do that with Cartesian variables. I'm going to switch to polar coordinates, which I did. This becomes 5 plus r squared, which is lovely. And then that's giving you a cosine sine, which is going to give you a sine 2 theta, which again integrates to 0 because you're integrating from 0 to 2 pi. Yeah. And then, of course, dA is r d theta. And then multiplying the r through, we've got ourselves at 5r plus r cubed integrated from 0 to 2 dr, which we should all be able to integrate. Of course, the question is, did you actually get to that, right? And the odds are against it at the moment because you guys are still learning. But there is partial credit, and there is 15 points on a 10-point quiz, so there is still hope. But let's see here. So yeah, 5r squared over 2, r to the 4th over 4, evaluate from 0 to 2. I think that gets me a 20 over 2 and a 16 over 4, which is 10 plus 4, which is 14, times 2 is 28 pi. So, yeah. Now, problem 2 I did wrong. But I liked the solution so much I left it. See, because I just assumed, first of all, I forgot to change that to an S. My bad. Sorry about that. I don't think you guys are really sitting and thinking, of course, this has never happened before today. Oh, how embarrassing. The CFAWs are here and the monitor's not working for the first time ever. Yes. So that was supposed to be an S, obviously, because otherwise I don't know what I would mean by surface integral with respect to a curve. That would be weird. But anyway, so the thing is, I completely forgot that I put z greater than 0 here, you know. And as such, I just integrated over the entirety of the sphere, letting the colatitude range from 0 to pi and theta range from 0 to 2 pi. And of course, rho hat dot rho hat is 1. And you just end up with r cubed d theta integrate. And so we did this in class, yes? For those of you who are not your first day here. We did this example in class, literally what I just did here we did in class. I don't think I pointed this out yet, though, which is, remember there's a divergence theorem. So the integral over the sphere is the integral of the divergence over the ball. And so the divergence here is 3, so I just get 3 times the volume of a sphere, which gives me 4 pi r cubed. Now this I did not tell you before, so I thought it was fun to circle back to that. But again, this is not really what you're supposed to do, because I said z is greater than 0, right? Which means that the colatitude ranges from 0 to pi over 2, not from 0 to pi. So that integral over sine doesn't go full 0 to pi, it goes 0 to pi over 2, which gives me a minus cosine from the antiderivative, which gives me a 0 minus a minus 1. Oh, wait a minute. Oh, man. Oh, no, it's the lower bound. So minus a minus 1, indeed. So it is, in fact, 2 pi r cubed. Anybody get it?
No question.
Ah, that doesn't sound like I got it. Yes, what did I do?
Why is it r cubed?
Why is it r cubed?
Same with the first one. Why is it r cubed?
Oh, well, there's one r. That's a good question. So the vector field that was given was f equal to x, y, z, right? And so that we could write as like the square root of x squared plus y squared plus z squared times x, y, z divided by the square root of x squared plus y squared plus z squared, right? And this right here is exactly what we call rho hat. It's the unit vector that points in the direction of the increasing spherical radius, right? And so if we're on, you know, on this, if we're on, given a point on the sphere of radius r, we have rho equals to r, right? But this is literally, the force here is literally rho hat. Like that's the formula for the sphere, the formula for this vector field in terms of the spherical radius, which would have been like super mean if I hadn't already done it in class, but I did. And
When we did it in class, the surface area was 4 pi r squared. But this is the flux.
but this is not the surface area.
Oh.
So, in short, when I put rho equal to r, the force actually evaluated on the sphere is r rho hat. So, Emily, like this is the force on the sphere is r rho hat. So going back up to there, I had that's just f evaluated on the parameterization, if you will, and that's the spherical, you know, area element, which we worked out r squared sine phi. And so that's why I had an r cubed, because this r times that r squared gives you an r cubed. Yeah. But you are right. The surface area was not that. The surface area was 4 pi r squared. Now this one, the last problem here, problem 3. Whoop. Thought you know, I have tried very hard to not allow notifications from Teams, but sometime I forgot to hit no, and now the Teams virus is popping up on my computer, so sorry about that. So here, this is the scalar surface integral. So S is a cylinder, right? And ds is just r d theta dz for this cylinder. And our parameterization, we can use theta and z for it. So x is equal to r cosine theta, y is equal to r sine theta, z is z. And so when I plug in the parameterization, I've got r cosine theta for my x, my 1 is 1. ds is r d theta dz, but we're integrating from 0 to L. Oh man, look at that. That's not good. Oh, I'm gonna have to take 2 points off my quiz. Can you guys tell me what's wrong with this? The bounds are reversed. Yeah, theta I've linked to the L, which is not right. This 0 to L should go with dz, and the 0 to 2 pi should go with d theta. So that's what I get for hurrying. But anyway, that integrates to 0, and the answer is still right, thankfully. But 2 pi rz, so we get 2 pi rl is the integral of that function. In other words, the integral works out to the surface area of the cylinder because the x part just integrates to 0 because it's symmetrically positive and negative on one half of the cylinder and the other. So that's why that happened. Any questions? No? Okay. So we were looking at Stokes' theorem, you guys remember. And so we talked about the proof of the Stokes theorem in the baby case, and that's, well, did it just? So I want to talk to you guys about the proof of Stokes theorem in the case that there are holes. All right. So actually, the argument I gave you guys last time will be the argument for us in here. I don't remember if I have a. I probably have a more, what's the word? Technical argument for like a graph or something after this. Give me a second here, guys. Yeah, let me skip ahead for a second here. So let's look at, I wanted to look at proofs. I wanted to look at Stokes' theorem's proof for a graph at the moment. And so what does Stokes' theorem say? Stokes' theorem says that the integral of the flux, rather, of the curl of a vector field, right, over some surface, right, is equal to the line integral of the vector field around the boundary of the surface. So this is Stokes' theorem, and we looked at a proof of it last time in terms of identifying that Green's theorem is true on like a little polygonal patch, and as if we had polygonal approximation to our surface, we could apply Green's theorem on each little piece and add it together, and that gives you one kind of sort of proof, and it's not a bad proof. But I want to just go ahead and prove this just for a graph, just to give you something a little bit more concrete and careful here. So a graph, we're going to look at the special case of a surface being a graph, because that covers a lot of ground, right? So we're going to say S is equal to x comma y comma f of xy, all right, such that what? xy is an element of omega. Now what's this omega? So like roughly speaking, a picture, what's going on here, right, is this is your graph, all right? And the domain for the parameterization is something like, you know, you can kind of visualize it down here, something like that. All right, and let's see here. What are the specific details of omega? So I'm going to make the proof as sort of painless as I can. I'm going to actually let my picture's not terribly far off, except that I haven't assumed 0 for bounds. So maybe my picture probably should look a little bit more like this. So the parameter range is letting a less than or equal to x less than or equal to b, and c less than or equal to y less than or equal to d, if I remember right. All right. And so this will inform how we set up the surface integral and also the integral around the boundary. So like the ds, kind of like you guys just did on quiz part 1, right? ds vector here is going to look like what? It's going to look like, oh goodness gracious, I just calculated it, I've already forgotten. My bad. 1, 1, what? Oh, my bad. I'm sorry, guys. I've forgotten my result. So when we calculate the cross product, so this is my parameterization right here, right? X of x comma y, if you will. And so if we calculate ds as partial x cross partial x partial y dx dy, what we get is minus partial f partial x minus partial f partial y and 1 dx dy. So that's the thing, the normal vector field in this case. So that's going to inform how I set up the left-hand side of this integral, right? So specifically, let me kind of just pick up the left-hand side of this for a second here. So the integral over the surface of the, oh man, curl of f. Oh, well that's going to sting. How does that go? So what are we integrating? I guess the xy integration is easy enough, right? So if I do CD integral a to b, what's the formula for the curl? So here we'll let f equal to PQR. All right, so the curl, remember, has 6 components that are formed from the partial derivatives of the components of the vector field as we calculated. And let's see here if I can find a formula for it right quick. We usually use the determinant mnemonic for it, don't we? But that is a little bit much here, but we've got partial y of r minus partial z of q, comma, partial z of p minus partial x of r, comma, partial x of q minus partial y of p. The last thing we're most familiar with, right? Because that one is the thing we've seen in Green's theorem already, right? Green's theorem in xy coordinates already has the z component of the curl in it. And then I'm supposed to take the dot product of this mess with the normal vector field, right? Which is, I'm going to use the x, that's like minus fx minus fy 1, and then dx dy. So that is explicitly what the left-hand side is, if we actually calculate it in detail in Cartesian coordinates here for this graph. What about the line integral? What's going on there? The integral around the boundary. So remember, we talk about this. How do we think about the boundary of S? That's the positively oriented boundary, right? So I told you guys, if you imagine a little dude, little dude. I don't know why they wear top hats, but anyway, so if you imagine him walking along the edge, if that's the positively oriented boundary, the upside of the surface, right? Which is the upside? Which is the top of the surface here? That's just defined by the normal vector field. See, that's how you know which way is up. So this says that the which way is up is in the positive z direction because of that 1 right here, right? So if I was to picture it, ds looks something like this. All right. And of course, that's not to scale since ds is an infinitesimal vector. That's probably too long. But anyway. And so if you imagine the little dude walking along, if he's walking in the positively oriented sense, then the surface will be on his left as he walks around. Okay, so like to draw the arrow, we're talking about it goes like this, then it goes like that, and then back here it goes like this, and then like that again. All right? So the boundary of S has 4 curves in it, right? The front and the back curves, they have x fixed and y as a parameter. The front, this curve and that curve, they have y fixed and x as a parameter. Let me use color. So like the red curves can use y as a parameter. The blue arrows here, they could use x as a parameter. All right? And so we can actually parameterize those edge curves using x or y appropriately, either freezing the other coordinates either at a, b, c, or d. Here's the details right here, right? Since I took so much of class time for your quiz, I don't think I'll have quite enough time to write all this out, but we can look at it together and understand it maybe. So C1, we have x equals to t, y equals to c. Where's C1 in my picture? Over there. Next to the x-axis. Yeah, this guy back here would be C1, right? And for C2, we have x equals to a, y equals to, oh wait a minute, that was C2. That was C2. My bad. I think, but that's not what you meant, is it, Sam? You meant this one, didn't you? But, so that would be C1, fair enough. And that C2, this is actually not C2, this is, well, depending on my notation, yeah, that's minus C2. Why is that? Because y increases this way, whereas the curve goes that way. And I'm using y as a parameter, so that's actually minus C2. C3, where's that? At y equals to d, so this would be C3. But it's not C3, why? It is minus C3. The reason for that is that it's going in the negative x direction, but I'm using x as a parameter, which means that this is actually the reversal of that curve because of the direction, right? It's going that way, x is going this way, it's the reversal. And then C4 is down here. All right, so 2 of the curves, I can just directly use the Cartesian coordinate as the parameter because it aligns with the direction of the curve. But the other 2, I have to reverse. Now, so that's the setup. And if you remember the proof of Green's theorem, this is going to be a lot like that. So here's a picture of what's going on. We've got C1, as you can see, C1, C2. Notice the arrow. C2 goes that way, C4 goes that way, C3 goes that way, right? See how the arrows are different on my board work over there? And so let's just look at look at the rest of the proof here, because it's somewhat involved. So what I do is I take the dot product, I actually carry out this dot product, and it gives me these three terms. All right? And then what we're going to do is we're going to break the problem into three pieces. Basically, we'll just let F1 be just the part with P, F2 be just the part with Q, and F3 just be the Z vector component of the vector field. Thankfully, the proof doesn't have any kind of interlinking between these three things. That actually just, each part stands alone, the proof part. So for the F1, when we calculate the part of the curl that comes from P, it's just that piece right there. So we have, this is from the curl. We have just these two terms that appear from this dot product. They're just two terms of the 6 total terms that appear there. And then if I actually carry out this integration, well, first of all, I have to do a chain rule. See, this is nothing more than the y derivative of the composition of the vector component P with the parameterization. See, because when we take y derivative, what happens is we get like partial P partial x times partial x partial y, which is 0. That's not even here. That's great, because it's not there. But, so like what I'm saying was when you take this partial derivative, you've got one term which is 0, which is fine because it's not there. The y derivative, well, we get partial P partial y times partial y, which is that. We get partial P partial z times the partial derivative of the z component, which is the y derivative of f, which is exactly what we have here. And you got minuses on both sides, so we pull it out. But anyway, the point is that this is the total derivative of that. Once you have a total derivative integrated over y, fundamental theorem of calculus just evaluates the thing at the bounds, which gives you the c and the d, like so. But that I put a star at because we're going to meet it in the middle. See, what I'm going to do is I'm going to show you that this piece is exactly what you get from the line integrals. Part of the line integrals, I believe. So if we look at the C1 and the C2, the C1 and the C2, or C1 and C3 rather, these guys, this guy and this guy, when you put in the parameterization and work out what the line integral means, well, we get this, which is exactly that, right? So apparently the integral of F1, right, the integral of F1, the flux from the F1 piece gives me this part of the integral around the boundary. And then, if we do F2, we can similarly show that it gives us the integral of the F2 around the boundary. And then you can do the same for F3, and so there it is. So it's really just to recap, the proof of Stokes' theorem, it really just rests on the definition of the curl, how you set up the surface and the line integral, and finally the fundamental theorem of calculus paired with a chain rule. But it's, yeah, the Z one is worse because it involves, yeah, it's worse. It involves both of the partial derivatives and a lot of chain rules. But there it is. So I think you see why I lead with the other proof, right? Because I think the proof that we looked at last class is way easier, right? Which is the one I should have given on the CFA day, but you know, whatever. If you guys have questions about the math major, feel free to talk to me after class. I can tell you things about why you should be a math major and not another major.